So NASA sees like some sort of speck of light in the sky, and based on the intensity of the speck of light, it has some guess as to whether or not the asteroid has a certain diameter. It gives you a minimum and a maximum diameter. And they're off by a lot. They're off by like a factor of 4 or something. So those are the diameters, like a minimum and a maximum diameter. And if those are the diameters, to get a radius, you would just divide by 2. And from there, we can use the volume of a sphere. And that's V equals 4/3 pi r cubed. So you would take the estimates that you were given for the large diameter, divide it by 2, use that for radius. That would give you the large volume, like the max volume estimate. And you would also divide diameter by 2, plug that into the formula to get the minimum volume estimate. So the big realization you should have from working with this data is that the estimates for the diameters of these things are pretty poorly defined. Like you have like huge factors of error between the minimum and the maximum estimate. Also, we're going to start fudging things because in real life these are pretty small bodies, you know, like meters across or whatever. So they can be shaped like this, right? They don't have to be spheres, but we're going to use spheres for the purposes of this problem. All right, so let's consider this particular body. It's labeled as 2010 TH19, and it has a minimum diameter estimate of 141 meters and a maximum diameter estimate of 269 meters. So that means that it's going to have a radius, a minimum radius of 70.1 and a maximum radius of 316. And I just got those by dividing these diameters by 2. And I'm going to be able to use those to calculate the minimum volume and the maximum volume. So if I substitute in the minimum radius of 70.5 meters into this equation, I would set it up like this. That's the volume of the sphere. And what I end up getting, once I do the calculation, is 1.5 times 10 to the 6th. So it's about 1.5 million cubic meters as a minimum volume. With that in mind, I can keep going and I can ask questions like what the minimum mass is. So what I ask is, what's the minimum mass? And I give a 3.4 grams per cubic centimeter estimate for density. And that was not easy to come by. You're welcome. I did have to like search around a lot for that, and I don't even know how accurate it is. But with that in mind, you would take whatever the value that you got for meters, and you would multiply it by 3.4, sorry, this is meters cubed because it's volume, 3.4 grams per centimeter cubed. And we actually want these lengths to eventually cancel out. So with that in mind, we're going to have to use a unit conversion. It's a pretty easy one. How many centimeters are in a meter? There's 100 centimeters in a meter. So I can multiply that by this conversion factor. And since I want to get rid of meters on the top of this giant expression, where do I want to put meters to cancel them out? On the bottom, right. I'm not going to put them on top to keep adding to more factors of meters. So I'll end up having meters in the bottom, centimeters in the top will cancel the existing centimeters in the bottom. It was 100 centimeters to 1 meter. And since it's cubed, I'm going to have to multiply this 3 times, right? Because I want to get rid of 3 factors of centimeters in the bottom, 3 factors of meters in the top. So that means I have to have this whole thing cubed. So once I go through that, I would end up getting a mass in grams, which is what I asked for. Yeah. So this will actually give you mass in grams, and then I have a couple more unit conversions which have to deal with converting those grams of just junk asteroid into grams of precious metals. So to do that, you would use the unit conversion of 28.3 grams of platinum group, these really expensive precious metals, for every million grams of asteroids. That's 28.3 parts per million. And I know this seems kind of exotic, but it's really just like any other unit conversion you're used to at this point. You'd have, well, first you have to remember what it is. It's 28.3. 28.30 grams of precious metals. I'll just call them PM. If you're not in this class and you're wondering what they actually are, they're platinum group metals. They're like rhodium, iridium, ruthenium, osmium, platinum, palladium. And that would be for every million, or 1, 2, 3, 4, 5, 6 zeros, grams of asteroid. Right, and you already have a mass of asteroid in grams from multiplying multiplying the volume of the asteroid by the density of the asteroid. So that would give you something in grams, and that's grams of asteroid, so it actually would cancel out with grams of asteroid in the bottom, and it would just leave you with grams of platinum group metals. So you end up multiplying your mass of asteroid in grams times the 28.3 grams of platinum group metals, and then dividing by the million grams of asteroid. And that's how you calculate how many precious metals are estimated to be inside of your asteroid. You'll do this twice, once for the minimum and once for the maximum estimate. And from there, there's another unit conversion we'll have to use to get from grams of platinum group metals to dollars. So what I quoted was, I think from a couple weeks ago. I don't think it's changed all that much, but I might be wrong. They changed a lot, so I don't really know. But at the time, it was about 28.77 grams per platinum group, or 28.77 grams, sorry, keep messing this up, $28.77 per gram of platinum group metal. And this was a weighted average based on a distribution that is found in meteorites times the market values for the different metals. I spent a lot of time on this, unfortunately. So $28.77 per 1 gram of platinum group metal times whatever you got from this part, which will be in grams of platinum group metals. So you multiply those, the units of platinum group metals will cancel each other out, and you'll be left with a dollar value. And these are going to be huge dollar values, and to be honest, I don't think the economics really make sense, even with some of the large asteroids, because there are questions like how long it would take to get this stuff to Earth, and there's also a question of, like, if you got this stuff to Earth, where would you put it? How would you get it there? I mean, I think if you got the stuff in orbit, what you could do is probably just toss it at Earth, like have a robot arm that just goes, flings it. But I don't know if you want that to be happening. Like, there are a few places on Earth where that's probably okay, but I think in general the environmentalists would be very angry with you. And if it was anywhere near people, they'd be really angry. So yeah, like you know, if you get it wrong, it's bad. Plus, there's also an issue of like Newton's third law. So if you're flinging material off this small rock, you're probably moving the small rock. So you probably have to have 2 robot arms, one on either side, or maybe 3, you know, at different sides of the asteroid, where you're flinging stuff strategically so that you're not destroying the orbit of the asteroid or flinging it into Earth. And you really don't want to be flinging large, you know, even asteroids like the size of a car. You don't want to be flinging that at Earth unless you want to have huge cataclysmic events. So it's interesting, but probably not of economic importance for some time.